think there is a time, so it's my great pleasure to introduce today's speaker, Dietmar Salamon. And he came from Zurich, and he is very well known from his many interesting works in symplectic geometry and gaze. The title is Uniqueness and Existence Problem in Symplectic World.
Yes. Okay, thank you very much for this kind invitation. So let's begin with the objects I want to discuss. There were two n-dimensional connected oriented manifold, and on it we have two forms. Which is symplectic, and that means that there's two properties, non-degenerate, that the nth exterior power is positive, so that means it uses the same orientation, and second, it should be closed. And first property means that when we construct a vector field with this two form, that gives us an isomorphism from the tangent bundle to the cotangent bundle. And therefore, from vector fields to one forms. And the closeness means that the Cartan formula simplifies to the Lie derivative of omega in the direction of the vector field being just the differential of this one form that we have here. And this immediately implies that we have plenty of vector fields preserving omega where this is vanishing. Namely, every closed one form gives us the unique vector field, and the corresponding flow will preserve the symplectic form. So this means that the group of symplectomorphisms of M and omega, or diffeomorphisms, preserving omega is an infinite dimensional group. And this condition that we have these many symplectomorphisms also allows to prove that every symplectic form in local coordinates is standard, so that's Darboux theorem that says that locally omega is always can always be written in the form some dxi which yi, if one can think of in physics as a separation into position and momentum variables. And another particular class of examples of vector fields that satisfy this condition that iota of x omega is closed are the Hamiltonian vector fields. So associated to any function from M to R, we have the vector field that we get a solid in the equation iota of xh omega equal to dh. So with exact one form, then we get an associated vector field preserving omega. And this leads to the subject of Hamiltonian dynamics. So if you look at these vector fields in these deRham coordinates, then the corresponding differential equation is the standard Hamilton's equation that x dot is dh dy and y dot is minus dh dx. And that's in fact also the origin of symplectic topology, as most people know. Coming from classical mechanics and studying Hamiltonian dynamics, and in fact there are many important results. Hamiltonian dynamics came out of the developments of symplectic topology in the last quarter of a century or so. But I do not really want to today talk about individual symplectic manifolds, but rather at the space of symplectic forms, or the space of symplectic forms. And one can think of that as the following inclusions. Let's take S to be the space of all symplectic forms, sitting inside the space N of all non-degenerate forms. And one can also, because these forms are always closed, one can assign a cohomology class to omega, a round cohomology class, or A, in H2 of the real operations. And then we can also consider a subset of all symplectic forms as A that represent a given cohomology class. So then the counterpart of having an infinite dimensional group is the question whether or not a given manifold M admits the symplectic structure. And if one does assume that M is an open manifold, i.e. non-compact, then the theorem of Gromov asserts, or theorem Gromov, that the H principle rules the situation, i.e. that these inclusions are homotopy equivalences on these infinite dimensional spaces when N is not compact. So that sort of pretty much answers the question of both existence and at least some version of uniqueness in the case of open manifolds. So let's therefore assume from now on that M is compact and has no boundary. I mean, the question immediately becomes much more difficult and a much deeper question if one assumes some kind of nice behavior of symplectic forms at infinity, and then the open case in that situation is quite similar.
So in this non-compact setting, the only invariants of the symplectic structure are
the topological invariants coming from all symplectic structures. Right. And that's sort of what the H principle does, is writing it as a partial differential. Equation and using these H principle methods to get this homotopy equivalence. So the compact case, of course, has at least one additional necessary condition is that the top exterior power, the product, also has to be non-zero and use the correct orientation, given orientation. And the second important fact is that the space of non-degenerate two forms is homotopy equivalent to the space of almost complex structures. And in fact, one can write down very explicit homotopy equivalence here using a background Riemannian metric. And in particular, associated to omega, one can consider almost complex structures J that are compatible with omega in the sense that if one plugs J into the second argument of our two form, one then gets a Riemannian metric. And the space of such J's is constructible, and therefore there's a second cohomology class that one can assign to omega, which is, I call it C1 of omega, but it really means it's the first Chern class of the tangent boundaries such an almost complex structure J, and that lives in the integral cohomology Z. So there are these two cohomology classes one can assign to symplectic form. And that also relates the subject to Kähler geometry, that in the case where this almost complex structure is actually integral. So the existence problem here would be given such an A, given an almost complex structure or a homotopy class of non-degenerate two forms, does it contain a symplectic form? And perhaps we're representing a given cohomology class, or wants to make a slightly stronger statement. That would be one question one can ask. And then there's the uniqueness question. And the uniqueness question has really very many facets. So one would like to understand given two symplectic forms and what are they equivalent, and one has to decide what equivalent means. And there are at least of 10 different equivalence relations. So let me mention some of them. Maybe the strongest is isotopic. So that means that there exists a path of symplectic forms, omega t, joining these two symplectic forms in the same cohomology class. So of course we need to assume that these also represent the same cohomology class. That's isotopic, and in that situation there's a classical theorem of Moser isotopy that guarantees that in this situation there exists a family of an isotopy, a family of diffeomorphisms preserving, identifying these forms. So that phi star omega t is omega 0. And so particular isotopic symplectic forms are diffeomorphic, but moreover by the diffeomorphism isotopic to the n. So then one can relate these conditions gradually, and for example, let's call it for the sake of today's lecture S homotopic, where one drops the condition that the cohomology classes are equal, so it's just a path of symplectic forms. And let me call it N homotopic, non-degenerate two forms. So even less stringent path of non-degenerate two forms. And then another condition is weakening the S homotopic. The condition is often called deformation equivalent. Meaning that there exists, that we allow another diffeomorphism. So there exists a diffeomorphism of M such that the symplectic can be joined by paths of symplectic forms to the pole or omega 1. So these are 4 examples of equivalence relations one can try to study. And
it might not be homotopically identical. So.
No, that's not required, right? If it is isotopic to the identity, then we are in the first case. So, let me state right away that there is the following open question. In dimension 4, related to the first equivalence relation, so one can consider the space of symplectic forms in the same cohomology class, and the question is, are they all isotopic, or to put it differently, is the space as A connected? And in dimension 4, that's a completely open question. So there's no single example where the answer is wrong. I mean, of course, there are examples where the answer is wrong when SA is empty. Right? But when SA is not empty. So let me maybe also mention here that sort of any of the known results about these equivalence relations require deep analytical techniques in the subject, like pseudo-homomorphic curves and cohomology, Seiberg-Witten theory, and also some explicit construction techniques. So let me begin with an example in higher dimensions, where an answer to this question of connectivity is known, and that's an example by Macduff. So it's a very simple manifold and a simple construction, but a difficult proof. A manifold is 2 torus times is 2 times is 2, and the symplectic form, the first symplectic form, is just standard symplectic form of this, where the two spheres have the same area, so even standard in this case, and the product symplectic form. And one can write down a very explicit diffeomorphism psi, given by, when we denote these variables by T1, T2, Z1 for the first sphere and Z2 for the second sphere, then it just preserves the first variables. And then, picture, if we use the element of the first sphere as to define as an axis of rotation in the second sphere, and then use one of the variables, T1 or T2, to define the angle, then we get a diffeomorphism here, rotating by the angle T1, and this diffeomorphism we hit Z2 with. So we get T1, Z1, and stay like that. So that's a diffeomorphism that acts as the identity on homology, and one can consider omega 1 to be the pullback of omega 0 under this diffeomorphism. And Macduff proved, so they both represent the same homology class, therefore, and Macduff proved that it's not isotopic to omega 0, this form, but it can be joined to omega 0 by a path of symplectic forms if we go away from this cohomology class. So if we change the ratio of these two areas and make them no longer equal, then one can actually find explicitly a path of symplectic forms, but not in the same with the same area. And she proved it using the modular space of pseudo-homomorphic curves in a smart way, cutting down the dimension to dimension 3 and using the evaluation map with values in one of these factors, and one of these has 2 factors, and use some kind of a Hop invariant to prove that you can't find an isotomy between these symplectic forms. And what breaks down is that if you change the areas, then you lose compactness for this modular space, and then the Hoff invariant argument no longer works. So that's why the proof breaks down, but in fact also one can construct explicitly a homotopy. So back to dimension 4. One can say a lot more about various related questions. Not about the question of connectivity, but about some other questions particularly about existence, using Taub's Seiberg-Witten theory. So let me just mention two consequences of Taub's Seiberg-Witten theory. One is a non-existence theorem that if we take an oriented connected sum of two symplectic four manifolds, x and y, so I want them both to be symplectic. Or more generally, we can assume that B plus is positive for both summands. Then there's no symplectic form from such a manifold, and the reason is that this Seiberg-Witten invariant has to vanish. And on the other hand, for symplectic manifolds, Seiberg-Witten invariants can never vanish. So that's one class of examples where one get non-existent, and there are many of these manifolds that satisfy the obvious necessary conditions. So I think of Taub's Seiberg-Witten theory of providing us with additional necessary conditions. Symplectic topology in dimension 4. And another simple corollary of these Taub's results has bearing on this uniqueness question. It tells us that if we have two symplectic forms in the same cohomology class, then necessarily, associated to these almost complex structure, the kind of canonical C structure, and these have to agree or be isomorphic, and therefore also the first chunk classes of the two symplectic forms. They are the same as the first chunk classes of the associated C structures, has to be the same. And in fact, the statement about the spin C structure is slightly finer than the statement, and it gives also in the simply connected case, there's some extra information concerning the sign of the Seiberg-Witten invariant. And, well, this information is there always, but in the simply connected case, it can be used because we know that when one is 0, 1 multiplicatively, then there are just two spin C structures associated to the same first chunk class, and Donaldson constructed an involution on the space of spin C structures which changes the sign. He proved that it changes the sign, the canonical involution coming from maps from S4 to S2. And this sign change means that the other spin C structure with the same first chunk class has the wrong sign of the Seiberg-Witten invariant, and therefore cannot carry any symplectic form. That's if B plus is big at least 2, and similar argument works also when B plus is 1. And so one gets that omega 0 is homotopic, therefore, as a non-degenerate two-form to omega 1. And that's if pi 1. N 1. That's the second consequence. And that has a bearing on the uniqueness problem. So it means in particular that no information can come from the first chunk class about our basic question here of connectivity of the space of symplectic forms representing the same cohomology class. To mention some more examples. I mean, some examples one gets pretty close to uniqueness, and that's for example with m equals 2. So there are various several results that play together in this case. So one is the deeper theory of clouds about the Seiberg-Witten invariant, which tells us that when the Seiberg-Witten invariant is non-trivial, then one gets holomorphic curves in an appropriate cohomology class. And in particular, this theorem implies that when we have any symplectic form, omega on CP2, that there exists a J holomorphic curve for any J, actually, sphere embedded in the class CP1. And once we have such a sphere, then there's a result of Gromov that if we assume normalized area of CP1 here, that there exists a diffeomorphism phi such that phi star omega is the standard Phrygian student form. And then there's a third result of Gromov. Another result of Gromov that says that for the symplectomorphism group of CP2 omega fs with the standard symplectic form, we know that it is homotopy equivalent to the isometry group PU3. And if one puts these results together, then it follows. It does not quite follow that the space of symplectic forms in the given cohomology class is connected, but it does follow that it is connected if and only if every diffeomorphism inducing the identity on homology is isotopic to the identity. So SA is connected if and only if the group, let me just call it if H of CP2 inducing the identity on homology is connected. And that's an open question, as far as I know, topology. And there are similar results for many other manifolds. Well, not that many, but same, certainly for S2 times S2, where also this connectivity of the symplectomorphism group, well, if they're the same area, it's not connected, they're components, exactly the right number of components, and if they're different areas, and it's connected by a result of Arbion and McDuff. And so therefore we won't get the same conclusion in this case of the equivalence of these two statements. Let me mention another example with autors. And here it is known that also by Seiberg-Witten theory that every symplectic form has to have first term class equal to 0. But in this case, the homotopy situation for almost complex structures and non-degenerate two forms equivalently is much more complicated. There's an infinite many homotopy classes of almost complex structures with the same first term class characterized by some kind of a Hopf invariant in H3 of the four torus. And it is not known if any two symplectic forms are homotopic as non-degenerate two forms in this example. And what I would call the torus conjecture, the four torus conjectures, classical four conjectures that the space SA in this example is always connected.
But it might be worth mentioning that on the four torus there are lots of almost complex structures for which C1 is not zero, but none of those can come about from.
And there are also all those, right? And they have no symplectic representative. But the conjecture is actually the weaker form of this conjecture is that only the standard homotopy class has symplectic representatives, or the two ones corresponding to the two orientations. And while we have conjectures, let me mention existence conjecture by Theorem and Lee. There's a nice paper about this circle from 2008 about the circle of questions for existence and uniqueness in dimension 4. And here he assumes in this conjecture that we have a minimal symplectic four manifold, so no exception divisor, not a blow up or anything, with which is of general type and has B plus at least 2. And so the general type contains omega, when C is C1 of omega, that C dot omega dot C is less than 0. And the conjecture says that if A, that the space of symplectic forms is non-empty, i.e. A is represented by the symplectic form if and only if A squared is positive and A dot C is negative. That's the existence conjecture, and as far as I know, there's no example where this has been completely settled. There are partial results, but for no example like that, it's instead full answers to this conjecture, as far as I know. So sometimes it is also interesting to look at the higher homotopy groups of the space of symplectic forms. For example, instead of just the connected components, at the fundamental group. And there's one result that has result by Seidel that has consequences for that. So, old theorem of Seidel from his PhD thesis, which says that under some conditions there are symplectomorphisms that are smoothly isotopic to the identity, but not symplectically isotopic to the identity. And one can say precise assumptions are four manifold that's assumed simply connected. Let's assume that the second Betti number is at least 3, and let's assume that there's a Lagrangian sphere inside of M, Lagrangian. So a sphere, so that embedded, and so that the symplectic form vanishes on all the tangent spaces. And then one can consider a generalized beam twist along the sphere. So it's a kind of natural generalization of what goes on in dimension 2, where you have a sphere and a manifold, and then you consider a diffeomorphism where you rotate the circle once around. And it's a gain twist, and that extends to the four-dimensional picture. And this gets called tau L, and tau L squared is smoothly isotopic to the identity. And not symplectically. And that's again a deep theorem requiring techniques of flow homology to distinguish the tau L from the identity.
Something wrong with this existence conjecture.
Sorry? What? Minimal. I didn't say minimal. Sorry. Oh, the existence conjecture.
For any cohomology class, A?
when a squared is bigger than 0 and a dot c is less than 0. These are the two conditions. These are the only known necessary conditions as far as I know. I think there's a result that I recently looked at by someone on this country. He doesn't fully prove it, but he looks at examples you get from gluing elliptic surfaces of odd degree, at least 5 or something, and I think he proved that it has a dense set represented by of classes represented by symplectic forms. I mean, I haven't checked the details of that paper. At least that was the assertion in both examples. So, back to this Seidel example. So, what it means is that if one looks at, for a moment, let's forget about the connectedness question and just fix a symplectic form, omega, and consider as omega to be the set of all rho, such that rho, of all symplectic forms, rho, such that rho is isotopic to omega, right? And then by Moser isotopy, it means it's related to omega by a diffeomorphism isotopic to the identity. So, so you get diff 0 of m divided by the automorphisms of omega in diff 0 of m. So by symplectic morphism of m intersected with diff 0 of m. Right? And now we see that here we have, by Seidel's theorem, non-trivial elements, so therefore there's a non-trivial loop in this space. Right? And this loop also, Seidel proved that if you perturb the omega a little bit, then it becomes isotopic to the identity. And what that means for this is that we have a loop of symplectic forms, non-trivial, but which is constructed in the space of non-degenerate two forms, but not in the space of symplectic forms. And there are many similar results also about higher homotopy groups using Seiberg-Witten theory in a nice paper by Peter Pronomo that's on his webpage, but as far as I know, it hasn't been published. And so it tells us there's some non-trivial topology going on in this space as well. Right, so then there's, maybe let me close this part of the talk with a question asked by Donaldson about symplectic form manifolds. It's related to many examples constructed by Ivan Smith and earlier by Taubes and McMullen, and also by Guiduzzi and by Ian and Parker, there had been a question around whether if given any manifold that has a symplectic, any form manifold that has a symplectic form, then are they all deformation equivalent under this weakest equivalence relation I mentioned before? And it turned out no. The answer is no. There are quite a lot of examples where the answer is known. Where this is whether so Ivan Smith constructed, for example, symplectic forms on the form manifold constructed in a smart way, where one first Chern class is primitive and the other divisible by 3, and more complicated examples of this kind. And so this shows that the first Chern classes are not even diffeomorphic in these examples. And the Donaldson question suggests the following: to look at two symplectic form manifolds x and y, and that these are deformation equivalent, that x and y are diffeomorphic if and only if. So deformation equivalent is too much to ask, but then one can make the product with S2 with the same symplectic form as S2, take the product of symplectic forms, and ask if they are deformation equivalent. the way deformation equivalence is defined doesn't really require that you work on the same manifold. It can be diffeomorphic manifolds, and then this question makes sense. And so that's question whether there are many interesting examples. So all these examples that I mentioned were not deformation equivalent here, they become deformation equivalent of the products. That's two. And manifolds, yeah, the same manifold, so it kind of confirms this is an interesting question. So what I want to say about this. So about examples, now I want to go and get on to the to the basic question of the connectivity of the space of symplectic forms in the same cohomology class on a hyperkaehler form manifold. There's a beautiful program by Donaldson to address this, and I want to describe this in the last 20 minutes of my lecture. And for that, as a little bit of background, let me make a little digression into moment maps. So here, the situation is that we have a constant Lie group G in the finite dimensional setting, acting symplectically on an omega, and then associated to this group action as the action of the Lie algebra of G into vector fields, which assigns, let's use the notation xi goes to x xi, which is a vector field associated to a Lie algebra element generating the one parameter subgroup. And the assumption here is to have a moment map is that this action not only preserves the symplectic form, but also the vector fields are all Hamiltonian. So i.e. I of x xi contracted with omega is the h xi, and the h xi is a function on m to r depending linearly on xi, so you can write it in the form inner product of mu with xi, where mu is some map from M to the Lie algebra, and I'm assuming here that there is an invariant inner product here on the Lie algebra, and that the moment map is related to the infinitesimal group action by this the formula. And I also let's assume that the moment map is equivariant, so mu of Gx is G mu of x, G inverse. And in this situation, an interesting thing to do is to look at the gradient flow of the moment map squared. And so I don't want to go much into motivation, but one studies, an interesting thing to do is to study the gradient flow of such a function. One can find out a lot about the geometry of this picture by doing that. So now there are many infinite-dimensional beautiful analogs of this picture, many introduced by Donaldson, and I want to explain one of them that has a bearing on this uniqueness problem, and I think a very beautiful approach to address it, and very difficult also. Even though the idea is actually very simple. So let me explain it in the hyperkaehler setting. So let's assume, so you get geometric flow. So let's assume that M is a hyperkaehler form manifold, hyperkaehler surface. So we have three symplectic forms and three compatible complex structures, so that plugging Ji into omega I always gives us the same Riemann metric. And of course, there are only two hyperkaehler surfaces, right? 4 torus the free surface. But as we know already there, the question is very interesting. So let's consider, for the sake of discussion, it's convenient to consider another manifold, even though it's diffeomorphic to M. And let's consider the space, the symplectic manifold, form manifold. And let's consider the space F of all diffeomorphisms from S to M. And let's consider the connected component where the pullback of omega 1 represents the same cohomology class as the form sigma on S. So this one is exact. Let's see the hypothesis. So that this singles out the connected component in space of diffeomorphisms. So then a group that acts on it, which analogous picture to this I now replaced the manifold M by this infinite dimensional space, and the group G by the space of symplectic morphisms of the source as sigma, and containing a subgroup G0, which is the Hamiltonian symplectic morphism of S and sigma. And in this situation, the space F itself can be viewed as a hyperkaehler manifold with the symplectic form written down in the obvious way. So if the tangent space of space the script F is just the space of vector fields along F, so omega 0 of S M. And if I take two elements, F1 hat and F2 hat in here, I can plug them into this one of the three symplectic forms, omega I, and integrate with the volume form over S, and then I get a number, which is bilinear form, and that's the symplectic form on the space of diffeomorphisms. So I get, call it omega, capital omega I of F1 hat, F2 hat, is simply, by definition, the integral of little omega I of F1 hat, F2 hat, which is a function, integrated against the volume form sigma, which sigma over 2 over S, right? And now this is a nice symplectic form, and clearly acting by symplectic morphism preserves this symplectic form on this infinite dimension space, and it turns out much more is true. The subgroup of Hamiltonian symplectic morphism acts by in a Hamiltonian way on this infinite dimensional space, and there's a moment map. So the G0 action is Hamiltonian, and in the analogy to this finite dimensional picture described over there. And the Lie algebra of G0, because we talk about Hamiltonian symplectic morphisms, is just a space of functions. So there's omega 0 of n, let's say, modulo really the constants, but let's not worry too much about this particular point. And then what we should get is a moment map, mu I, which goes from the space F, assigns to every F a function on F, right? And here's a formula, mu I of F is just the quotient pullback omega I, wedge it with sigma, and divide by the volume form of sigma. Right? So this formula is a moment map for this action. That's a little calculation. After you have the definitions, you can just check, verify these properties and see that they're satisfied in this case. Right? And also it's easy to see that this is an equivariant moment map. And then, so the thing to do in the hyperkaehler setting is to take the hyperkaehler and take the sum of the squares of the three moment maps, right? But three symplectic forms, three moment maps, let's take the sum of the squares, and then you get an energy function on the space of functions by taking the L2 norm of each of these functions. So let's take half integral over S of the sum of the norm squared of these functions, f star omega I, where it's sigma, divided by volume form of sigma, and integrated against the volume form of sigma, 3. Right? And so one can consider this space of functions, and now it is functional on the space of the homomorphisms, and now take the L2 gradient flow of this function. That would be the next step in analogy to this finite dimensional picture, and then one ends up with a nice sort of flow on the space of diffeomorphisms. And well, let me write down the formula for this differential equation. So one gets dTft is equal to the sum 1 to 3 of ji df composed with the vector field x sub hi. So this formula here, where hi is precisely that function, f star omega I h sigma divided by volume form sigma. So this is the differential equation that we'll try to study and see what comes out of this. So now, as in the finite dimensional picture, the gradient flow of the moment squared is invariant under the group action. So here we started with the Hamiltonian group, but it's actually invariant under the bigger group G of all the symplectic morphisms, and therefore one can push forward the diffeomorphism Ft, the function, the symplectic form sigma under the diffeomorphism St, and then one gets a path, instead of diffeomorphism, one gets a path of symplectic forms on the target manifold N. And so this push forward leads then to a differential equation on the space of symplectic forms on M. So we define the power of rho t by pushing forward sigma under Ft. That is the parts of symplectic forms representing all the same cohomology class A. Right? Omega A equal to omega 1. Right? And the differential equation that shows up here has the following form. dt rho is equal to minus the sum from 1 to 3 of dki rho composed with ji rho. And the ki rho here is just a push forward of h, and what that means is that ki rho is is omega I wedge rho t divided by the volume form of rho t, i.e. rho wedge rho divided by. So that's the function ki, and the ji rho one gets by using rho on ji, plugging ji into rho, and put ji on the other side and call it ji rho. So that's the definition of ji rho. And this equation here, this is the Donaldson geometric flow on the space of symplectic forms on a hyperkaehler manifold. Right? So the right-hand side is certainly exact. So it's a differential equation for symplectic forms in the same cohomology class. And one can try to study that. And so, first observation, I don't have time for very many observations, but one of the main observations to understand this flow is the following: that first of all, there's the push forward energy function. So the energy over there is, of course, by equivariance the same for any two equivalent Fi's, and this means I get corresponding energy function for this rho. That can be rewritten in the following way as 2 times the integral over m of the self-dual part squared of rho divided by rho plus squared minus rho minus squared, because rho is symplectic form, this denominator is positive, and integrated against the volume form of the background hyperkaehler metric. So that's the first effect.
So the self-dual is, and any self-dual parts are also with respect to the background metric.
Yes, with respect to the background metric. And then the next interesting observation that is very important for understanding this gradient flow is that for every rho, there's a very nice metric associated to a rho and the background metric. So one starts with any Riemannian metric on a form manifold in any symplectic form, and then one gets a metric which I'm going to call G superscript rho for now. Right? So that's a metric on M associated to rho, and let me just say 2 things. One is that the Hodge star operator of this metric on one force is given by rho, which Hodge star of the background metric of rho dash lambda. Now that's an isomorphism from 1 forms to 3 forms, and this isomorphism defines a metric, a Riemannian metric on M. And then another thing that is very interesting about this metric, and that's related to this formula, is that if I consider a self-dual 2-form, any self-dual 2-form, and if any such 2-form has the form property, self-dual for the background metric, that omega of there is a J, or the J defined by this formula is an almost complex structure. That's the same as self-duality. And then it follows that if one defines omega rho to be omega minus the same function k that shows up here, omega west rho divided by the oil rho times rho. I forgot. Right? So one makes this construction. So it turns out that this map that assigns to each omega this form is actually an involution on the space of 2 forms, and that it preserves the pairing, the wedge product. And then one defines J rho in the same way, and one gets that omega rho, that's over there, of dot J rho dot, gives us always the new metric G rho. That's the second important property, this kind of compatibility of this form with that almost complex structure. So now one can also define that using this metric, one can define a Riemannian metric on the space of SA, on the space of symplectic forms. And this metric has a form, so take rho hat to be the tangent vector of SA. That's an exact form, and write rho hat as d lambda, and choose lambda in such a way that it is the smallest norm with respect to that metric. So this means star rho lambda is exact, and that is unique, right? And now you define the norm of rho hat squared with respect to this rho to be the integral over n of lambda, which star rho lambda, or as the norm squared of rho which lambda. That's not the same. So if one does this, then it turns out that this equation is the gradient flow of this function with respect to that metric. Right? And furthermore, I have nowhere used in this part that the manifold is hyperkaehler. And so that's one of Donaldson's observations in his paper, is that the whole story carries over to general symplectic manifolds. At least formally you can write down the equation. And let me just give you the formula for the equation in general. And then I start. So the general Donaldson geometric flow is the following. It's dt rho equal to d star rho d. So this is our star operator in three forms. No comes in one form. No comes in two form. Then after d we get a three form. So the two form we take can either be written as a formula, let's say minus rho minus squared rho plus rho plus squared rho minus divided by a function that I like to call u, which is just the volume form of rho divided by the background volume form. So we also have to take a background metric. And then we get this equation. And this term here, that's here in brackets, can also be geometrically thought of as the orthogonal projection of star rho onto rho per. So it's a little calculation that if we orthogonally project the Hodge star of rho onto the orthogonal complement of rho with respect to this standard pairing, then we get this formula. And this equation is the general Donaldson geometric flow, and it's the hyperkaehler case equivalent to that equation.
This is the background star?
Sorry? Yeah, that's the background star. When the star is undecorated, it's the background metric. So one has to fix the background metric also to make sense of this energy function of this situation. So that is what naturally comes out of the picture. And now I have minus 3 minutes left, and in these minus 3 minutes, I want to make minus 3 remarks. So the first one is so Donaldson's observation that in there's a unique absolute minimum of this function, and the Hessian is positive definite of this absolute minimum. The second remark is the energy controls the L1 norm of rho. Third remark is in the hyperkaehler setting, if I take any other critical point of this energy function, then the Hessian cannot be positive definite. There are four vectors coming from the hyperkaehler structure, the critical point that one can find so that the sum of the Hessian on these four vectors is equal to 0. So at least one direction. Either they are all 0 or one direction has to be negative. And now let me also point out that since we know that, for example, in the K3 stuff with the Zeiberg theorem applies, there's a loop of symplectic forms. So if there's any meaning to this, i.e. if the analysis works for this equation, then there got to be some of the critical points. And there got to be one appendix 1 in the K3 surface so that the flow can, so that we get a circle, which is determined by a non-trivial circle that Zeiberg theorem provides. And many other critical points coming from this Conner theory. And finally, you mentioned that so I had a student of mine, Robert Tom, working on this geometric flow, and so far we didn't get much further than Donaldson in this paper from 12 or 13 or more years ago. But at least, so he has now proved the local existence and uniqueness for this flow equation. That's already pretty hard. And the regularity, at least on some non-sharp assumptions.
So short time existence.
Short time existence and uniqueness and regularity, but so far the assumptions are not sharp, and this proof involves very much this Riemannian method that shows up here. It's associated to raw effect. It's a very important reading for the whole story, and I could say more. Involved two-dimensional analog, which is also very tricky of this story. I also mentioned in this paper of Donaldson's diffeomorphism moment maps, but I think I'm going to stop here.
So is this flow strictly parabolic, or?
Yeah, that's the problem. That it looks kind of parabolic, but it's rather non-trivial to prove it. I mean, in the original form, in equation 1, it's you have this big infinite dimensional group acting, you get rid of it there. But and a nice way to understand this is to replace rho by the three functions k1, k2, k3 that show up as the equation in the hyperkaehler case. But there's a kind of non-trivial correspondence between these three functions and the rho. And these three functions look very much like a rather complicated parabolic equation, but three functions live kind of in a codimension three submanifold, three coming from B plus of the space of all functions, and that makes the whole thing very tricky.
Just a comment. I think I have a counterexample to this conjecture of generally.
Oh, really?
I'll show
that's interesting. Maybe I misunderstood.
Yeah, no, I was just
blamed here to me for giving the wrong conjecture. I mean, maybe I misread his. Maybe I misread his conjecture. I have to look at it.
It's some constructions in the usual instance.
May I ask about this problem about if you have a different manifold after multiplying S2?
Yes.
So if it is 2, symplectic manifold has different homogeneity invariant, then definitely after multiplying S2 is still not symplectic model.
Yeah, that's sort of one of the ideas behind this question, that the cohomology invariants, the hope that they carry over to be symplectic invariants in the sixth-dimensional setting. But it must be quite subtle, because if you take values... No, only for the... But I think it must be very subtle, because there are these examples of Ireland Smith, right? Where the first joint classes, one is divisible by 3, the other is primitive, and then if you take the product of the two torus, something breaks up. Right? So there's... because they're still not... no, maybe not something breaks up. Wrong. It fits with this. But it's still not deformation equivalent, even though they live on the same manifold. Right?
So it's higher dimension than the other. Actually, I don't know so much if there is so much.
No. In the high dimensions you have two symplectic, dimension 6. In this example of Dusa, you have two symplectic forms that are not deformation equivalent.
So
in the same cohomology class, but they do not come. It's also on the product as T2 times S2 times S2, but they do not both come from a symplectic form on the
So you multiply S2, they get the same symplectic form?
I don't know. I do not know.
Probably area is very small, probably it can be said, right? Because the example, the point is that this 2S2 has the same area, right?
Yeah. And if you change the area, it's very subtle.
Yeah, so
you cannot capture it with
if you multiply the third one, which is the same area, still survive? Hope invariant is so stable.
I don't know. But if you multiply it with a higher torus, then it survives. Then the non-normativity form survives. But I don't know what happens if you multiply with other manifolds. And I should also mention there's some more recent paper. This you guys do this quite old, but by Seidel in 2011, where he has a more fancy construction of a similar kind, I think. But when he uses Fukaya categories also to construct in all dimensions, I think on symplectic manifolds in the same cohomology class that are not isotopic to each other.
So another question is about this process. What do you expect if everything works?
Well, if everything works, what you expect is that the flow line converges to the unique minimum, right? And then the minimum is unique, that's omega 1, right? And so therefore, the flow is in the same cohomology class, and therefore SA would be connected.
So if
everything works, you can pass by all the other critical points if there are any.
Yeah, but there are context.
No, let's say it's a completely open question on dimension 4.
So this way to try to prove that problem.
Yes,
Okay.
in the hyperkaehler setting, for example, for the photors or the K3 surface at least, the hope would be that this is an approach to settle the uniqueness question in these some examples. And then, of course, one would also expect that, I mean, all kinds of things can go wrong with this flow that goes off to infinity or something, and one would expect that this might happen when in some other examples, but absolutely nothing is known in relation to it.
Perhaps we should go ahead and thank Dietmar again, and I think a lot of people have questions in private, so maybe this is it.
If you need to see the parents to up this, let me know. And guys, just do this question.
So, the kind of so according to Benjamin's definition, you say that.
Yeah.
So a general
Oh, not easy. You choose.
Yeah, I'm good. Yeah.
Well, put down what here. So, the hypothesis is that you have a symplectic manifold. So we don't need to do it. Oh, okay, that's that. So B plus gets that.
Well, no. What do you mean? There's two terms in the
B plus. He said, no, that's unless you want to say, yeah, but if B plus is different power. Okay, now where is the unit?
If it's nearby, then I can come because I can.
So it's the height of
This is automatic.
Well, you have great examples. So when he says general type, I mean, it's actually got this idea, but it's much greater spot. So there are quality cool kinds of examples. So Taub's shows that, in fact, minus C1, this is always represented by some.
Yeah, the restaurant is ages to get food.
Now, the thing that's misleading about the complex in the case where it comes from this signal will be connected. But there are many examples in Conjectures and Stern where, in fact, this is not a connected. Most people so in these hypotheses, you can find examples far away in Stern where you have as many connected components as you like. So when you take the canonical class, you have some.
And you're saying you can get counterexamples of this?
Yes, maybe because if you had any. Yes. Because if you have, it has to be positive on all of these.
No, wait, I don't understand what you're saying.
So instead of having...
You're saying they all correspond to non-trivial variables.
Yes.
Yeah, but there's a theorem that the variables only see. That's the...
For a complex surface of general type.
Yeah, that's what I'm saying.
Well, but tangentially, when he says a symplectic manifold...
No.
Oh, but in the Taylor case, I mean, it's sort of almost. So certainly you already have a Taylor coming, right? So
yeah, but is it the same?
Well, no, because you still have that's still only in H11, right? But then you can add on. So you take a Taylor class and then add.
Yeah, but are you saying the symplectic corresponds? I don't think so. I think it's an open question. Whether or not. Every class with A squared bigger 0 and A with C negative should win. I don't know if that's. You're saying that's the Taylor form?
No, because the Taylor form is after all contained in H11, which is a proper subspace.
Yeah, the union of all Taylor forms is this? I think that's all.
Well, no. In fact, sometimes the complex surface is rigid, right? It might be that you can't do it.
Yeah, so the conjectures, these classes.
But you can take something like this and then add on principle. The real part of some homomorphic form.
Yeah, right. But then the question is whether each class is represented. That's the question.
Yeah. So,
and I think I don't.
Yeah. I agree. So
oh, these are symplectic and non-Kähler.
Yeah.
No,
but so this
it's not the right conjecture.
Right. So yeah. So Chen generally sometimes has this terminology of talking about Canary dimensions of.
Yeah. That's another story. But here,
this is general type.
Yeah. But this is not.
So it's definitely
general type.
So it's definitely
not this symplectic extension of the mode of general type. That's certainly not. No, the Kähler case were already second proof that there's only one exception, one basic class. That's the assumption.
Yes.
Only one basic class. And that, of course, is the reason for making this conjecture. If you have more basic classes, of course, you wouldn't have made the conjecture.
Yeah. So the amusing thing is that it resulted for a long time. If you took a symplectic manifold with these hypotheses, no one knew of an example where the anti-canonic.
Right.
But it's now known. We now have lots and lots of examples.
Okay. So
there are many different.
Yeah. Okay. Then we understand. Yeah. Right.
So
that's not the assumption. This is classical stuff that came out in the first written paper on this, I think.
Yeah.
That the canonical class is the only one who's non-trivial that are good.
Right. So I mean
these general assumptions and that situation. That's where the
right. So even when you take things that you build naively out of so I mean, you certainly get interesting symplectic forms by taking, if you take the Kähler form, and take the real part of a sufficiently small holomorphic to zero form, then, so that right. So if it's but the problem
you get some, you get away from the Kähler form for sure, but
But even in the Kähler form, you have the problem that you still have holomorphic curves for a given complex structure, and so among the Kähler classes for that fixed complex structure have to all be positive on any holomorphic curve. Right? So you can definitely get
you're suggesting there are other constraints? I don't know.
But on the Kähler classes, I'm just saying in terms of what I can do.
Okay.
So
but for symplectic forms, I mean, you could conceivably get away to a different J where the holomorphic curves is right? I mean, and so because the Gromov invariants are only non-trivial for this.
Yes, right.
So that's the reason for minus C. That's the reason why Kendra makes.
Certainly that's.
So it seems to me a reasonable conjecture.
It's the only constraint you can easily see.
Right.
Yeah. So.
Because it is,
So I find these kind of examples fascinating because it's sort of it really illustrates the degree to which when you get away from the Kähler world, I mean the fact that the canonical curve has to be connected is very interesting to a complex case, and it just doesn't break down in the symplectic world.
This is sort of related to that question you were asking the other day at lunch.
Oh yeah. I explained that to Dietmar as well. Symplectic hypersurfaces, do they satisfy the simulation step?
Right. Yeah, I just asked Donaldson question at lunchtime. Whether the complement is always Weinstein.
Yes.
I think he said he didn't have the answer offhand, but he thought it should be true.
Okay. So that's the Donaldson hypersurfaces.
Yes.
But I asked a question for.
I'm sure I can't do dinner tonight, but my wife teaches math.
And you have a long ride.
My daughter will go hungry if I don't go and make her some.
Yeah, we don't want to be responsible for that.
You can ask the same question for general hypersurfaces, right? So, I mean, take I don't know, a degree. Let's say take a degree 3 symplectic. Let's say a degree 4 symplectic hypersurface in CP3. Is that simply connected? No, the hypersurface itself. That's a consequence of having this Weinstein thing. So degree 4 hypersurface CP3, is it simply connected?
That's the question. So you don't want to do using universal equivalence.
But I would do 3 or less. 4 is.
You describe
What do you mean? The symplectic hypersurface given by a section.
So
degree 3 line bundle, which.
So just, I mean, its point radial is represented by 3. I mean, its homology class is 3 times the height, 4 times the hyperkaehler. So that's the only constraint. So that's the question I was asking you, because it's much more general than Donaldson hypersurfaces.
And is it not obvious?
It's not obvious.
That if you have 2 components, that the intersection number must be positive and therefore. The intersection number is non-zero.
Intersection number
of 2 symplectic submanifolds. By 2 symplectic surfaces.
of degree 4.
No, it doesn't matter what degree. It's just take 2 symplectic submanifolds of.
And then the intersection number is
positive, so yeah, that is it.
Right.
I would say for CP2 the answer is obvious.
But what does intersection of 2 hypersurfaces have to do with the fact that
They cannot be
they're
disjoint. Sorry, I thought you wanted to disjoint.
No. Pi 1 is 0. That's what I want to prove or disprove.
Pi 1 is 0 of.
So maybe I can write it down. It's easier. So
Yeah, but CP2, CP3, you know.
CP3.
So,
yeah, so you have some symplectic hypersurface.
oh, can it be a union of 2?
So
The union of 2 intersecting a surface, that's what you want.
let me write this down. So symplectic.
I'm not understanding the question.
It was quite one of us to be 0.
Its homology class is 4 times the homology class.
And you want it to
of
be a submanifold. You have 2 connected components.
Is pi 1 s 0.
But you asked if you have the surface itself as 2 connected components, or what?
Nothing about connected components. Just say it's connected. Assume it's connected.
Okay. That's the question.
Is pi 1 s equals 0?
Oh. That's